So very happy that being able to be here and have fun discussing with people here. So this is sort of a way to introduce myself. Actually, you might recognize that there is some similarity in the title. The last year I gave a seminar around this time of the year. This is like a progress report. So since then so last time I presented the result of a couple of papers I have written on this subject. Since then I have written 2 more papers, so twice as much material. And so this will be a totally different talk, and but a similar title. So this is a follow-up on the talk I gave last year. So let's see, it works.
Click on it.
Click on the screen.
Yeah, I can just touch this. Oops. Ah, yes. I guess the reason was that it wasn't. Yeah. Thank you. So the idea is the following: that suppose you have a conformal field theory or quantum field theory more generally, and suppose it has some kind of global symmetry. And the global symmetry means that you have the symmetry that is actually acting on the Hilbert space, non-trivially, as a unitary operator. And so if you have such situations, then it's useful to decompose the Hilbert space into irreducible representation. That's what we learn in undergraduate quantum mechanics, for example, that you decompose the energy eigenstate into irreducible representation, say, of rotation group to solve a hydrogen atom. And if you are Pauli, you can even decompose that into representation of SO form. And so I'd like to present some universal result that I point out that if you go to high energy, then all unitary quantum field theory behaves in the same way as far as the symmetry decomposition is concerned. And so I'd like to present the formula for this. And in particular, I will discuss high energy asymptotic behavior of density of state and 3-point function in conformal field theory and their decomposition with respect to such symmetries. So last year when I gave talk, I talked about these 2 works with Daniel Harrow and Monica Kahn and Jehari. And I had some follow-up work with David Simons-Zafin, Nathan Benjamin, and Jehari. This is about 3-point function. And also some work by Yuyakusuki, Sarah Mauriciano, and Shrudeep Paul. So this is about entanglement entropy. And so I would like to discuss those results. So I have structured the talk in the following way. So the first 20 minutes or so, I will present all the results. So I will give you a bunch of formula and explaining what I mean by the universal asymptotic behavior in high energy. And if you're interested in these results, then the remaining half an hour or so, I will explain what proof methods I use to derive these results. Okay, so that's the sort of structure of my talk. So I'm going to first present the result without explaining where they come from, and so you can decide, and you are welcome to leave after 20 minutes or so. Let's see. This is not working quite well. That's kind of slow. No? First of all, if you don't do the symmetry decomposition, then we of course know the universal behavior of asymptotic density of state by just doing the thermodynamic argument. So if you calculate Poisson function, so beta is the inverse of temperature, then the leading term in high energy should be should obey the thermodynamic property, and in particular it should be extensive exponential of Poisson function is a free energy. It should be expensive, so that means that it should be proportional to the volume of the Cauchy surface, which I didn't write it, but there is a volume of Cauchy surface. So, but if it is conformal field theory or in general in any unitary quantum field theory in high energy behave like conformal field theory, this should be dimensionless. So that means that it should be multiplied by temperature to the d-1. And this constant C is depending on the choice of theory. For example, in 2 dimensions, it's proportional to central charge, and so this is a Cardy formula. And so if you do the Laplace transform, you can also calculate the density of state or degeneracy of conformal primary operator for large conformal weight delta. And so basically the Laplace transform of each other. So we can easily understand this type of behavior by just knowing, by just using the standard thermodynamic behavior. So this is like undergraduate physics. So what I would like to discuss today is to decompose this formula to refine it with respect to symmetry. So instead of taking the trace over entire Hilbert space, we can restrict this trace to particular state in Hilbert space in particular representation, or insert some projection operator into representation. So the question is that how is this high energy Hilbert space decomposed into irreducible representation of global symmetry, or also space-time symmetry, like rotation group, etc. And so that's what I'd like to explain. So
can I ask a question?
Yes, sure.
Just out of curiosity, is there an expansion of this formula, the first formula before symmetry enhancement for asymptotic free theories?
Asymptotic free theory, yeah. So if you have asymptotic free theory, then ultraviolet, you have just a bunch of free bosons and fermions, and then you can calculate these things.
So I have in mind the gauge theory, and you say in that case, it just count the number.
Yeah, you just this just count the number of photons, for example. If you use the pure gauge theory or pure Mills, for example, then this She will be proportional to the dimension of the gauge group, for example. And they're multiplied by some constant which you can calculate by using free photon Paschen function. So yes.
And when you talk about space-time symmetries, so you are having in mind that you always put it on a sphere.
That's right. So here I have in mind putting theory on sphere times time, and then rotation symmetry. So if it is in d dimension, decompose the Hilbert space into representation of SOD. That's what I have in mind.
But for the asymptotic free gauge theory, the subleading behavior is going to be very different.
Right. Yeah. So I will tell you how to calculate the subleading behavior. So in fact, one of the technological improvement I'm introducing is to give you a systematic way to calculate the subleading terms.
But do people understand this thermal effective theory argument for asymptotic free gauge theory? For asymptotic free theories like gauge theory?
Yeah. Well, asymptotic. So we are expanding it near the free point, right? So I suppose we can do it. But for specific theory, I think we need to discuss.
I mean, there's a conformal anomaly. So.
Right. Yeah. So for example, the leading correction probably you can calculate using. I guess it depends on dimensions, probably. Yeah. Yeah. Actually, even this coefficient C in general is not. If it is an interacting theory, like. It's not easy to calculate. If it is asymptotic free theory, you can calculate it. But if it is general CFT, non-trivial, which is non-trivial in ultraviolet, this is not easy to calculate. In 2 dimensions, you can calculate it because there is a UV-IR relation by modular invariance, so you can relate it to the anomaly. But in general, it's not so easy to calculate C. But there is some C, and I'm going to tell you that if you know what C is, then you can calculate everything else. Okay, so the first result is this one. So if the theory has some discrete group symmetry, so the absolute value of G is G is a group, and supposing that G is a finite group like Z2, Z3, or whatever finite group, then absolute value of G here is a number of elements of the group, and I say that here is a counting of total number of conformal primary operator. And then if you ask, well, what is the number of primary field restricted to some representation, so this is the result. So we say that it's proportional to actually dimension square of the representation. And this is normalized so that if you sum this over all the representations, unitary representation of the group, this sum up to 1, so that the formula is consistent. This is this is the kind of formula that you teach in undergraduate group theory. So this is related to the Planck measure. So this follows from the fact that if you insert a unitary group a unitary operator associated to the group element G. Then for high temperature, it actually favors trivial elements. So if these two statements actually are equivalent, as I'm going to tell you. And so this, I'll tell you how to derive this one. Okay, so this is a result for finite group. So then you can naturally ask, well, what if G is a continuous group? So in particular, here I'm interested in compact Lie group. So how does this formula generalizes? Well, you can see that immediately there are some issues with this formula, because first of all, the number of elements of the group is infinite. In fact, continuous infinite for continuous group. So the denominator is infinite. But numerator can also be problematic because there are infinite number of representations. So it's how you don't normalize this is problematic. So that means that this formula has to be regularized in some way.
So if you sum over the representation of this, which we call the original formula?
Yeah, so for this one, yes, this just follows from the orthogonality of characters. Okay. So remind you that there is this thing called orthogonality of character. So if you sum over representation, G, chi I, sum over representation. So suppose chi of R is a character, and R is a irreducible representation, and then if you have this, then for finite group, you have this property, and then suppose I substitute. Oh, I guess it should be properly normalized. So it should be like G or something in it, and then if you set G1 is equal to G2 is equal to 1, then this becomes dimension square. So this from this you can see that the dimension R square summed over representation is a number of elements of the group, and so therefore this is properly normalized. Okay, and so you can ask, well, so there must be some kind of regularization going on when this is a continuous group, and then this is what this is actually. So you still have dimension R square. So this is like finite group, but it has to have some kind of regularization. So that means that for large representation there must be some kind of cutoff. And in fact, we can see that there is a cutoff. That C2 is the second Casimir of the representation. And so if you fix the representation and if you take delta to be large, then this is going to go to 1. So basically, you recover the fact that it's proportional to dimension R squared, and times the full density of state. But if you keep delta fixed and R large means large second Casimir, then there is an exponential decay in this. So that's how the regularization takes place. This is actually the leading correction for large delta. You actually have subleading term which has higher moment Casimir, so like fourth Casimir, etc., or square of second Casimir would appear if you calculate the subleading term, which you can systematically calculate. So K is another sort of constant associated to the conformal field theory. So different conformal field theory has different K's, different B, B. And so for example, in two-dimensional conformal field theory, if G is compact Lie group, then if the symmetry is a Lie group, then in fact you automatically have Kac-Moody algebra associated to that group. And then in that case, B is actually related to the level of Kac-Moody algebra. So it's characteristic to the what kind of theory. So just compare this. So for finite group, we had this formula. For compact Lie group, we had this formula. Both are sort of proportional to dimension of the representation square. But for compact group case, you have some kind of regularization factor to take into account the fact that you have infinitely many representations. So this is normalized so that the sum of R actually sum up to 1. Yes.
So the P prime, you didn't tell us in higher dimension where it comes from, but it's always positive.
So yes, I will explain why this is positive. Okay. Yeah. And also I will tell you how to calculate this P prime from thermal effective field theory. So P prime is related to a term in the thermal effective field theory. Yeah. So
the dimension of JPs. It's still divergent, right?
Sorry?
There's a dimension.
Oh, this is finite. So for example, SO2 it's 1, SO3 it's 3, and things like that. So it's finite.
It's not yet.
So this is the number of elements is for compact. Okay, and we derive this formula for any unitary conformal field theory. But if conformal field theory happen to have gravity dual, then this teaches us about black holes. So for example, even this simple formula is interesting because suppose you have a gravitational theory in ADS, and suppose the theory has fermions in it. Then any such theory has Z2 gauge symmetry associated to the fermion number. So if you have fermion number parity, that you multiply -1 to the F to everything. And so then you have Z2 symmetry, and according to this formula, so number of elements is 2 for Z2. And so that means that you have, for large energy, you have almost exactly the same number of Z2 even state and Z2 odd state. That's what this formula tells you. And for that means that suppose you have a large black hole in unitary space, and then you can ask, is that black hole fermionic or bosonic? Then we say that almost half of microstate of the black hole is fermionic, and almost half of the microstate is bosonic. I didn't assume supersymmetry, but asymptotically for large energy, there are almost equivalent same number of fermions and bosons. And so this is there's actually a very nice paper by Joaquin Triaci and Yimin Chen, I think, that actually they discuss a phenomena which is sort of more refined version of what I just told you. They calculated the ordinary Poisson function of black hole entropy and also the index. So index would be constant if you have supersymmetry, but if you don't have supersymmetry, the -1 to the F trace over e to the minus beta h is not constant, but they calculated the exponent, and they indeed get the result consistent with this. But if you're just interested in whether the leading term cancels or not, this is actually sufficient to actually show that you have almost exactly the same number of boson fermions for large energy. So this is already teaching us something interesting about black hole. Okay. We can also calculate decomposition of study decomposition of entanglement entropy and the entanglement spectra with respect to symmetry. And this is something that actually condensed matter physicists and the statistical mechanics people are interested in. And in fact, Sara Murciano is a student of Pascal Calabrese, and she's working on statistical physics. And the question is the following. So suppose you have a Cauchy surface of conformal field theory and divide the space into some region and its complement, and then you can calculate the entanglement density matrix and calculate the von Neumann entropy associated with it. So this is a standard calculation that we are all familiar with. But then if the theory has symmetry, you may consider decomposing this density matrix into representation of the symmetry. So you can, but to do that, we can do the following calculation. So in order to properly do that, we have to actually specify the boundary condition here. So the modern way of calculating it is to consider this as like the boundary conformal field theory calculation, where we introduce symmetry preserving boundary condition over here and here, and then calculate annulus amplitude like that. And then we can calculate what's called Renyi entropy. And if you take the limit of n goes to 1, you will calculate the entanglement entropy.
Can I ask you something?
Sure.
You say symmetry preserving here, in addition to conformal symmetry, you have in general this Kagmuri thing. So
right.
It's been like J bar equals 0 or
so here, so that's right. So if you have, for example, the continuous symmetry, you have some, this is 1 plus 1 dimension, then you have what you may call Ishibashi state associated to the Katsumudi algebra.
And some faces or something like that.
Yeah, so I think there is a general construction of how to do this. So for any primary state, you can construct what's called Cardy state. And you can do that for Katsumudi algebra too. And so the formula I'm going to, so in general, there are actually choice of boundary conditions in general, there are several different boundary conditions, all of which satisfies the symmetry. But the formula I'm going to write actually is independent of choice of boundary condition. The dependence on the boundary condition comes in the subleading term in the formula. So the formula is very similar to the one that I gave you earlier. So in the limit when q goes to 0, q can go to 1, which is the limit when the boundary shrinks to a point. This is the limit we want to calculate, and we can actually obtain this type of formula. And this is very similar to the formula we obtained earlier for the density of state 2. So and then there was a question about a rotation group, and we can also decompose the Hilbert space into representation of rotation group. So this is, in this setup, I'm assuming that, that we are putting conformal field theory on the cylinder. So the Cauchy slice is d-1 dimensional sphere, and then you have a Euclidean time going in the time direction. And then we can decompose the Hilbert space into representation of SOD. And so L is an angular momentum generator for rotation. Omega is what you may call angular velocity. So it's a chemical potential for the angular momentum. And then you can decompose that into irreducible representation of rotation group. So L is the angular momentum. So you can calculate these things. There is some kind of discussion about the Kashmir energy, but I will skip that in view of time. And then this is the formula. So this is actually to simplify. In order to write this formula on this single slide page, I restricted here the case when I only turning on one of the angular momentum component. In higher dimension, in general, there are several angular momentum components. But I'm just showing this so that we can show that there is a formula for this. And so we can calculate the density of state for primary field of conformal weight delta and angular momentum. So this is a general formula that we derived. And this generalizes the Cardy formula in 2 dimensions. So in Cardy, in 2 dimensions, you just have conformal weight and angular momentum. Delta plus L is what we sometimes call H, and this is H bar. And so this is a standard Cardy formula. It generalizes to higher dimension.
Like is F.
So F is related to C. So F is just one coefficient which we need to calculate in order to calculate the asymptotic behavior. But this is related to C that so this F is related to the central charge. Another question I often get is what happened to the D equals 3. But in fact, in D equals 3, if you take the limit of D equals 3, this actually becomes finite because this vanishes. So that means that this goes to 1 over D minus 3, but this also goes to 1 over D minus 3. So in fact, this is finite in that limit. And so this is a formula.
What is epsilon D?
Sorry?
Epsilon.
Yes, epsilon D was defined in the previous slide. So this is the Casimir energy on the sphere. And so this is related to the conformal anomaly in even dimension. In odd dimension, it's actually epsilon D is there.
Just to be clear, this delta is the eigen, when you write the conformal group as the cover of SO2D is the quantum number of SO2. So
that's correct. So another way of saying it is that we are looking at the geometry where we have the cylinder, that the Cauchy surface is SD minus 1, and you have Euclidean time. And in that case, delta is just the eigenvalue of the Hamiltonian. Okay, so here is a summary of the formula that, so this is for finite group, this is for compact group, and this is for the spatial rotation. We also derived the asymptotic behavior for the 3-point function of the conformal field theory. So you can decompose a 3-point function into conformal blocks. One of the technically interesting and challenging thing for higher dimension is that even for 3-point function, there are several conformal blocks. because the rotation group is no abelian. So in 2 dimensions, so those familiar with 2-dimensional CFT think that 3-point function has only one terms. But in higher dimension, you have several conformal blocks, and so you have to calculate the conformal blocks. So that's why, for example, the OP coefficient is 3 depends on this formula. And one thing, so I'm going to explain how we derive this. But one thing I wanted to point out is that you had this question about F. So this F is something that appears in all these formulas. So once you know this single parameter F, then you can actually calculate everything that is of interest. So and the reason for this is that all these terms come from a single term in the thermal effective field theory that I'm going to derive. Okay, so this is a presentation of my result. As I promised, this was 20 minutes, and so if you are interested in how I got this result, you can stay on. Otherwise, I will not be offended if you decide to leave. And so I would like to actually explain how we got this result. Okay? So two important ideas is a Noether theorem and the effective field theory. But we decorated this by saying generalized Noether theorem and thermal effective field theory. So I would like to explain what I mean by this. So let me start with the Noether theorem. So this is actually based on this paper by book called Duplicia and Longo. These are mathematicians, algebraic quantum field theory people. And so actually Ed Winton told me and Daniel Harrow about this paper when we were working on symmetry in quantum gravity. And so this is the following idea. So let me briefly remind you what the Noether theorem is without this generalized things. So this is just this following idea that if your quantum field theory has global symmetry, which is a compact Lie group, the continuous group, then there is a Noether current J, which is one form, and which is conserved. And then for Cauchy surface, you can integrate this and then define unitary operator. So that's a sort of Noether theorem, right? And this is what, in a modern terminology, this is a topological surface operator, codimension 1 topological operator. And but this form already suggests that if this Cauchy surface is decomposed into disjoint subregions, if this Cauchy surface is a union of some disjoint subregions, then because this is an exponential integral, this becomes product of unitary operators associated to each region.
And R's, do they have boundaries?
Yeah, these has boundaries. Yes. So one of the things they did very carefully, these algebraic people, algebraic quantum field theory people, was to discuss how to deal with this. And the idea of their proof is rather intuitive, that they consider some kind of projection operator. So you start with the algebra of local operator in the entire Cauchy surface and consider some kind of restriction onto some subregion. And basically project this operator into subregion, and that's how they define this operator. And non-trivial technical part is to show that this is well defined and unitary and then etc. So that's what these people
But
did.
when you say disjoint, you don't allow the
Overlap. Yeah. So
Also the boundary.
if it is the overlap, then you have to decide which part belongs to which.
But also don't allow touch, have common
They can
boundary.
touch each other, but they have to know which part belongs to which.
Does the individual U still have some topological property left with?
It's invariant under homotopy deformation, actually homology deformation, but keeping the boundary fixed. So it's like I don't know, soap bubble or something. You can, so suppose you have the region Ri, then you can deform the region like this, but you have to keep the boundary.
Yeah, that's very intuitive, but do they actually have an explicit definition of U in terms of bulk integral on the region with boundary and some other boundaries?
There is an earlier paper where they discussed the continuous group case. I think some subset of the authors had some papers where they actually, so in their paper it's actually very explicit. They consider some kind of integral, they actually discuss integral and how to regularize it on the boundary, etc. But in this paper, they do very abstract thing. And they do that because they are interested in generalizing this for discrete group too. So what I mean by generalized Noether theorem is that you cannot generalize this notion because there is no Noether current for discrete group. But this identity can be generalized. And that's what these people did. So what they did was that supposing you have more general group. So G is now, G can be either a continuous group or can be discrete group. But even if this is discrete group, this is true. That they show that even for discrete group, you can actually define sort of restricted symmetry operator associated to each region. And so that you can take product and obtain the unitary operator which generates a symmetry. So as I said, this is obvious for continuous symmetry because of this Noether current, but this also holds for discrete symmetry. And yes.
To what extent this UI is unique? Because probably there is some ambiguity which can be can reshuffle.
Yeah, so there is a question of what exactly you do on the boundary. I think that's a tricky part of this definition, I think. So for example, if R is compact, I think there's a possibility of trading operator between different trading operator between boundaries. So this was what actually Daniel Haran used to prove that there is no global symmetry in Euclidean space. And so when we are trying to prove it, we first had a proof for continuous group, and we are wondering whether we can generalize it for discrete group. And Witten told us, well, there is this nice paper that you should use them. So we should listen to him. And so that was a generalized Noether theorem. Okay, so nice thing is that you can generalize what we believe to be true about Noether theorem even for discrete group. And so this is very helpful. The other idea is the thermal effective field theory. So I learned about this from the paper by Shiratsu Miwara, although probably there are some earlier paper on that subject. There's also a very nice paper by Zohar Komargovsky where he applied this idea to calculate some supersymmetric index. So here's the main idea is the following. So if you are interested in doing some finite temperature calculation, which I'm doing right now, so one way to consider it is to consider compactifying the time direction into circle of circumference beta. Okay, and then if you are interested in calculating high temperature behavior, then you should be taking the limit when beta goes to 0. So the obvious thing one might consider is that since we have this small circle, so you might consider some low energy effective theory on one less dimension, on d-1. So that's the idea of the thermal effective field theory. So from the point of view of d-1 dimension, suppose for example you calculate generic 2-point function, then because of the thermal disturbance between the 2 points, you'd expect that 2-point function would decay exponentially. And so this is called thermal mass. And so in general, if you have generic operator, then the particle propagating between the operator would acquire mass of at least of order beta, of order temperature. And so there is a decay of 2-point function by exponential of minus temperature times the distance between the point. We expect that to be true in general. There are exceptions to it. So I think that the only exception I know of is actually massless free scalar field. So in that case, suppose you put the massless scalar field on this geometry, then in one dimension lower, you still have massless free scalar field in low energy, the dynamical degrees of freedom. And so that's an exception. But as far as I know, that's the only exception I know. For example, in massless free fermion, if you choose thermal boundary condition, then the fermion gets mass, the energy gap in low energy, of energy gap of order of temperature. So in generic situation, therefore, there will be no light degrees of freedom left in low energy on d-1 dimension. So that means that the effective Lagrangian depends only on the background field. So what are the background fields? Well, so So if you have, oh, I apologize. So here I'm using G for the metric in d-1 dimension, whereas I'm just below here, I'm having G for the group. So I apologize for the abuse of notation. And this small g is the choice of the element of the group. And so this background field depends on this choice of metric. But also, if you insert operator u of g in the trace like we did before, so this is u of g. So we are interested in inserting this u of g in the trace. So that means that there is a holonomy. And in d-1 dimensional point of view, that would be like adjoint scalar field. And so the cosmological constant term can depend on the choice of this group element. And then there are many other terms that you can write down in low energy effective theory. The kinetic term for the scalar field G, or the Yang-Mills field strength square, etc. But these are all suppressed by 1 over t squared. So this is actually the leading term. So we just need to calculate this to understand the leading high temperature behavior. So moreover, we can do this for any geometry for sigma g, because so low energy effective theory is local. So as far as you provided that you write this in a diffeomorphic invariant way, then this v of g is universal, independent of the choice of the geometry. So I'm going to use this fact to argue that this is actually related to the Kashmir energy of the twisted sector of conformal field. So by that I mean the following. So if this is a summary effective field theory, then if you are interested in calculating something like that, where you insert u over g, h to the minus beta h, then the leading behavior of this is calculated by calculating this potential, or the coefficient of the cosmological constant term. And then the rest is proportional to this. So like I said, I can put this on any geometry. So for example, what I'm going to do is the trick that we are very familiar with in 2 dimensions, which is the following. So suppose this d-1 dimensional space has one more circle in it. And then we have now the full geometry has 2 circles, the original thermal circle, and then new circle from the Cauchy surface. And then basically I'm going to switch between them. I'm going to exchange them. And if you do that, then you can relate this to the Kashmir energy of the G-twisted sector of the conformal field. So here is how we do this explicitly. So the geometry is so that we have this thermal circle S1 of beta, and then you have another circle S1 of beta tilde, and then you have the rest of the Cauchy surface. And inserting u of g means that you wrap this topological operator on this S1 times beta, and also wrap it on sigma d minus 2. And then it's located at a point on this thermal circle. But if you swap these 2 circles, you can see that the geometry is so that now we have this time direction here, and this is now part of Cauchy surface. And then this unitary operator, or the topological surface operator, is located at a point on this. So that means that you have a domain wall which implement the action of group element u of g on this point on Cauchy surface. So this is like twisted sector in this direction. And by doing the appropriate rescaling of the geometry, you can see that indeed this quantity is proportional to the volume of the Cauchy surface times the circumference of the time direction. And so therefore, this must be the Kashmir energy density for the twisted sector. Okay, and then in fact, you can use the unitarity of this operator to argue that this Kashmir energy density should be non-negative. And but in fact, by using generalized data theorem, we can actually prove the stronger statement that if G is a non-trivial element, this is strictly positive. So supposing this is the case, then we got into the following situation, that this is a calculation of a thermal partition function using thermal field effective field theory, and we have this dependence. And then when temperature is very large, this is going to grow exponentially, or there is minus sign, so this is going to decay exponentially. if B of G is positive, but except when G is trivial, in which case this is going to be 0. So that means that for large temperature, that trivial G is favored exponentially. And so therefore, we obtain this formula. So now this is something we learn in undergraduate mathematical physics, that for finite group, the Kronecker delta in the group element can be expanded into some of the characters. And from this, you immediately obtain this.
Can you say some more comments on how you prove that B is strictly positive?
So B is strictly positive. So we can actually easily show that B is non-negative, but to prove it's strictly positive, you use generalized Noether theorem, which basically follows from the fact that you can actually, so the idea is that you want to show that the Kashmir energy is non-zero for the twisted sector. And so basically you can use generalized Noether theorem to construct an operator to create the Kashmir energy from a twisted sector. And then you can show that if U of G is non-trivial operator, which this is, because this presence of U of G can be detected by charged operator, then this operator has to have non-zero energy. And so that's the kind of argument that we are writing up. And from this, it is follows. Okay, so now, if I asked a question about B prime, which is actually related to this B thing. So in the case of compact group, what we can do is that we can expand this in near the identity operator. So you write G is equal to e to the I phi, where phi is some kind of adjoint scalar field, and then look at the quadratic term. Linear term vanishes by symmetry, and the quadratic term, so this inner product is given by the killing form, and then we can write it in this way, and then by using the argument similar to the one that I gave for finite group, we can show that B is positive, so we have this property, and then so you can do the basically what you do is that do the Laplace transformation of group decomposition of this function into characters. So the idea is that this is a class function of group elements, which means that this function is invariant. Yes.
This at the maximum when phi is equal to 0. So
B is maximum at phi equals 0. Yes, that's why it's negative.
But so that's opposite of what happened for discrete groups, where if V of 1 was 0 and the other.
So the V is maximum at identity, and otherwise it's exponentially suppressed.
You're saying V is non-zero and positive when G is not equal to.
Oh, I'm sorry. So let's see. Did I mess up the sign? It's possible I messed up a sign that. Let's see. So I might have messed up the sign. Maybe that. Yeah. You may be right that I must have messed up the sign, that I might need minus sign. And but so this is meant. It is meant. I meant that this is an exponent for this one. So since I defined B to be minus of the exponent. So I think I had the sign wrong here. So thank you.
And that is the volume of the boundary of R that appears in this expression. So you have a region. I mean, I don't know how to interpret this sign. R is a region of the Cauchy surface.
Oh, I'm sorry. So yeah. So this formula is wrong for two ways. The sign is wrong, and by volume I meant the volume of this thing. I apologize. So I had this transparency there. And okay, so what I wanted to say was that this is by definition this is invariant under conjugation of G by another group element. So if you replace G by H inverse, this is invariant. So that means that this function we should be able to expand in terms of characters. And the way you can fix this coefficient is there are various ways to fix it, but one way to fix it is to notice that this satisfies the heat equation on the group manifold. And this also satisfies the heat equation on the group model. And so from that, you can actually derive this formula easily. So this is what we obtained. And by Laplace transform of this relation, we obtain this formula. Okay, so I think we have 15 more minutes, so let me move on. Oh yeah, so I had to discuss some examples. So we can actually check this formula for for compact Lie groups for various examples. For example, in the U1 case, you can test this for free scalar field and free spinors. I told you that for free scalars there is a problem because thermal effective field theory does not quite work. And so what's going to happen is that if you look at the free scalar field in low dimension, this formula is actually not true. That there is a deviation from the formula. There are terms which depend on the log of temperature. And we can explain that by noticing that there are 9 degrees of freedom after compactification. We can also test this formula for counting the Bekenstein-Hawking entropy for charged black hole in unitary space. And so we thought that people in general relativity must have studied this. So we tried to look at the literature. There are a couple of very nice review articles on the Reissner-Norton black hole in unitary space, and written by GR people. But it turns out we discovered that there are actually some kind of outstanding puzzle in the classical general relativity literature, which was the following. So suppose suppose G is no abelian D algebra, and so that means that the boundary CFT have the global symmetry G. But that means that in the bulk you have Yang-Mills theory with gauge group G. So that means that in order to calculate the high temperature behavior of this kind of partition function with group element inserted, you would like to calculate the density of a state, or you would like to count the microstate of black hole for this no abelian gauge group G. And then there was a puzzle that which was the following. So there are actually 2 classes of charged Reissner-Norton black hole for no abelian group. So one is that to notice that, as I said, this is actually a class function, which means that it's invariant under conjugation of G. So in particular, for given G, you can actually turn G into maximum torus of the group. So namely that in the direction of Cartan subalgebra of the group. So if G takes a value in this maximum torus of the group G, then you can pretend that gauge group is actually not G, but is actually tensor product of U1 raised to the power of rank of G. And you can actually construct the Reissner-Norton solution of a given charge by restricting gauge field to be the abelian direction. Then you can just use bunch of you can use the standard abelian Reissner-Norton solution to construct the black hole solution of required charge quantity. Okay, so that's one solution. But GR people discovered that there are actually also genuinely no abelian solution in which the gauge field in the bulk do not commute with each other. So you have different component of the gauge field, and then in general you can construct a solution of which the no abelian gauge field do not commute with each other. So this has been an outstanding question in GR community. There was some debate about which one is more stable or not. And we can at least answer this question in the regime that we are interested in. It is for the following reason. So suppose you go to high temperature, then the black hole in unitary space grows. The size of the horizon grows and go toward the boundary of unitary space. But near the boundary of unitary space, because of the gravitational effect, all the field decays exponentially. And so that means that the distinction between abelian gauge field and no abelian gauge field disappears, because the difference between them is in the nonlinear interaction term in the Yang-Mills Lagrangian. So that becomes irrelevant in the infrared. And so that means that in the high temperature limit, the 2 solutions should converge. And somehow GR people didn't know this, but when we inserted we use their solution, which is the numerical solution, and compare them. As actually we can check that these solutions actually do converge. And once we know that, then we can start from that limit and then calculate the free energy for these two classes of solutions. And we can actually check that the non-abelian one is more stable. So then using that, we can calculate these F and B coefficient for in these cases.
So this is 1 over temperature tax or the
Sorry?
this 1 over temperature means higher derivative tax and the
That's right. So this is correct. So we can. So if you can, not higher derivative corrections, but the finite size correction of the black hole. We can still work in the Einstein plus Yang-Mills Lagrangian, but you can calculate. You can take into account the leading interaction term, leading correction by the Yang-Mills interaction.
It's related to Gabriel's question. This F and B, by your argument, should be the same for both solutions.
That's correct. Yeah. So for large temperature, yes, because it's a high temperature. Yeah, that's correct. And yeah, so in view of time, maybe I'll skip this discussion of calculation, and then so let me discuss how we calculated this decomposition into spins. So that was sort of another adventure for me. And so this is actually inspired. So we got this idea from the paper by Nekrasov. So Nekrasov had this calculation of proof of Seiberg-Witten solution to M equal to gauge theory in 4 dimensions. And so they use what they called he called omega background. So essentially we're going to use the omega background. Is that basically this calculation is omega background calculation. So as you go to the as you rotate around the circle, you rotate the sphere by some angular velocity. And so then this is like Caltech ansatz, but then there are off-diagonal elements. So we can calculate off-diagonal element in this omega background. And the interesting thing is that there are denominators like this. And so then we can substitute that into action, the summary effective action, and calculate it. And then in the limit of high temperature, it becomes of this form, where you have some kind of polynomial dependence on temperature and angular velocity. But the interesting thing is that there is this pole in the denominator. And the pole appears in the limit when omega becomes I. And that is a limit when the black hole is the black hole. If this was a rational Norton black hole, the black hole is rotating at the speed of light. That so when black holes rotate at the speed of light, this diverges, and so therefore the contribution of omega equal I comes from the limit when the delta minus L goes to small compared to delta and L themselves. So this is very much like light-like limit of conformal field theory. So in this limit we can actually do the saddle point to do the Laplace transform and calculate this quantity. And so this is how we got this result.
What is the non-convergence property of this trace on the complex planes?
You mean that the inverse transform, or
not just the convergence of the trace for complex orbitals?
You mean this one is convergent, obviously, but
just at the pole.
So you mean that at the pole?
No, what's the general convergence property of this trace for complex orbitals?
Well, let's see. So what happens is that in CFT, the unitarity bound L minus delta minus L.
Yes.
Right. So delta has to be greater than or equal to L.
Yes.
So if omega has imaginary part greater than I, then this can become negative. And so therefore, this is a limit where this is the omega equal I is on the verge of this start diverging. Right. So what I meant was that since delta is bounded by L in the spectrum, so we have H plus I omega L. So if some component of omega is I, then the real part of this eigenvalue can become negative. And so therefore the trace may start diverging. And so I think this existence of this pole is a reflection of that divergence.
But the unit disk will be convergent.
Even in the CFT on the unit disk, you have divergence if you do that. Is that a puzzle?
Wait. So
Oh, you mean disk, not sphere?
No, yeah.
What do you mean by disk?
So the reason I ask is because, like, in 2 dimension, you have the convergence equals beta left and beta r.
Right. Oh yeah. So in 2 dimensions, yeah. So you can analog of the statement in 2 dimensions is that you can calculate the trace of e to the minus beta L naught minus beta bar L naught bar, for example.
Yes.
And but beta and beta bar has to be positive in order for this to be convergent.
Yes.
And you can ask what happens when beta goes to 0, and keeping beta bar non-zero. And this is something we worked on. Yes. There is some interesting behavior for the how the singularity appears, and this is consistent with this.
Rotating black holes, and I thought also charged black holes in EDS generically have superradiant instabilities. So how that shows up?
You mean the rotating black hole or the charged black hole?
Well, I like rotating black holes in general, even in flat space, in the presence of massive particles, which would be here in the bulk, right? But I thought also charged black holes in EDS. There was this Gopser story about.
So you mean with some scalar charge scalar?
Right. Yeah. Right. So, generically, this superradiant instability appear.
Right.
So, which kind of would indicate probably that that's not the 2 minimum, right? In the dual series of black holes. So how does it?
Let me see.
The gaps is going to depend on the temperature.
Well, it depends, but there is a.
I think that's the limit just there. So this is the limit of, I think, parametric inside of the superradiant instability limit of mid-1, right? Very galaxy.
I'm not sure whether that instability appear in this context.
But parametric, I think it's important. Delta minus alpha for the square of down.
Not sure.
Maybe a better question. What is the physical significance of this parameter regime?
So the significance of this is that we can do the calculation.
But
in this regime we can calculate and obtain this result.
The camera is saying that coincides.
And then
Nathan telling me so also.
sorry?
I remember Nathan.
Unfortunately, so what we really wanted to do was to do this calculation in the limit when L minus delta goes to 1 of order 1, which we unfortunately we couldn't do quite. So that's why we were only able to go up to here.
But that's a future limit, it's not a black hole limit.
This is not a black hole limit, you say. Why do
When
you say
delta
that?
minus L is around the 1, no? It's like this higher.
Oh yeah, so that's not a black hole limit. Yeah, so we are interested in that limit for some
That's the
other
super
reason.
rate.
Yeah. Okay, so yeah, so this we checked this result also is consistent with Cardy black hole entropy calculation in ADS. I think the result is independent of whether there are other, in addition to Einstein term and Yang-Mills term. I don't think the result depends on whether there are other fields or not. So I think that this super radius instability is a different regime, but yeah, I need to think about it.
Because curved black hole it doesn't have the presence of some massive fields,
Right.
and becomes unstable. So maybe it's in some different directions.
In ADS.
Well, it's already in flat space.
Yeah, but in ADS it's different, right? Because if some massive particle carries the angular momentum away, it's confined in ADS potential. So in fact, the end result is a rotating black hole with cloud of
Yeah, but that's what
rotating particles.
Right, but that's what
This calculates.
This superradiance does, right? So
Yeah. So if that's what you're worried about,
Right.
that's what we are calculating. Namely, that it's not the entropy of isolated black hole, but isolated black hole with additional sort of crowd of low energy particles. That's what we are calculating. And there is a difference in that. And in fact, I plan to comment on that. Yeah, you have a question.
From the perspective of your formulas, how would you tell the difference between a CFT with a bulk dual and one that doesn't have a bulk?
So this one is true for any CFT, and when it has a bulk dual, then it agrees with bulk dual.
No, I understand, but is there any way to so you're saying you can't? There's no diagnostic to distinguish between the two.
No.
Because you're saying even looking at subleading orders.
Subleading, I do not know. So subleading term may tell the difference. I don't know. Leading term is the same. There is only one number f, which is related to the Newton constant in the bulk. So f is related to the Newton constant in the bulk, and so I think that this is there is no difference between this for the CFT with. So this is true for any CFT. So in particular, true for CFT with the bulk dual. There is no diagnostic of the CFT without a bulk dual. The reason for this is that for high temperature limit, the black hole becomes very large. So any sort of correction to Einstein gravity is suppressed by inverse power of temperature. So that's why the subleading correction can tell. But even if you calculate subleading term, you can still reproduce that with Einstein gravity coupled to with correction by R square or R cube, etc. So you can still parameterize this. Yeah, so maybe I can comment on your question later. So this is basically the summary of this, and then so we can actually also calculate a 3-point function with large conformal dimensions. And so the idea actually comes from the two-dimensional calculation by Cardy, Maloney, and Maxfield. So in two dimensions, what they did was the following. So they consider genus 2 conformal field theory on genus 2 Riemann surface, and they calculated the limit when this 3-cylinder becomes very thick, very short and very thick. So that means that in that limit you have the very high energy state propagating through this cylinder, and then in that limit you can relate this to square of the 3-point function times the high energy density of state, and then you can extract this quantity. And so basically we generalized this for a higher dimension. So what we did was, so this is called Whittaker-Schottky parameterization of Riemann surface. Basically what you do is that you consider pair of two spheres with 3 holes removed and then connect them by cylinder. So basically we repeated that for higher dimension. And then in the limit when beta goes to small, so we can do the thermal effective field theory calculation. So I just passed 3, so maybe I'll skip, I'll go quickly, but in the limit for small temperature, you can actually use the same thermal effective field theory to calculate the genus 2, the asymptotic behavior of the genus 2 Halcyon function. And then from that, we can extract these coefficients. So that's sort of the result.
Sorry, but these are the coefficients for some generic 3-point functions that given.
That's correct. Yeah, that's right. So basically it's smeared because we are calculating it in sort of Laplace transformed form. So you can when you go to the basis with fixed conformal dimension, we are smearing out this granularity in general. So another thing I wanted to say, maybe I should say it here, was that here we are using this conformal blocks for primary operator of conformal algebra. And but in 2 dimensions, for example, if you try to do the same calculation, you have a choice of whether you do this calculation for global conformal primary or the Virasoro primary, and you get a different answer. And if you choose this conformal block as that for the Virasoro primary, then you are actually really calculating the micro 3-point function of the microstate of the black hole. Whereas if you calculate if you use a conformal block for global primary, then you are allowing the boundary gravitons. So then in general, this would be like calculating the effect of the cloud of gravitons also. So I think this may be related to Sergei's question. So namely that when you calculate this thing, whether you calculate 3-point function of the black hole in the bare black hole without the cloud of gravitons, or whether you take into account the effect of the cloud of gravitons, they have a different behavior. And in fact, in 2 dimensions, it's kind of interesting because if you actually calculate this, including the boundary gravitons, then actually 3-point function becomes bigger. So there is a puzzle of how to interpret it. There is actually an interesting paper by Rob Meyer and collaborators recently about the interpretation of this from the amplitude for merge of the two black holes.
And sorry, here the deltas are the same for all 3 operators? Because I see a single delta.
Oh, yeah. Here I simplified this. So in order to fit that into, so in general you can have different deltas, and but here I simplified this so that I can put that in a single place. And so this is all I wanted to say. This effective field theory is like a telescope that you can see in the high energy by observing it from distance, and then from that we can derive all these formulas. So thank you for your attention. Yes, please.
So for the 3-point function, do you, again, can you only derive 3-point functions of generic operators, or is the way of refining these formulas and selecting some particular class?
Well, so refining, depending on how you do that, but if you have additional global symmetry, we can consider refining it for decomposing it to representations. Another thing that one might ask is that, well, so there are some sort of very sophisticated work by Sasha Zhiboidov and others about worrying about how to do this Laplace transform. That in general, the genuine behavior of 3-point function will not be such a smooth function, but it's more like a granular function with various signs, etc. And but when you calculate the 3-point function in this way, we are sort of doing the we are calculating the basis of temperature and angular velocity, and we are summing over all states. So we are sort of smearing over this kind of granularity. So in such a situation, one might worry that we are missing information when we do this Laplace transform. And then they have some method of using Tauberian theorem, etc., that how to sort of estimate the correction.
So, I mean, this formula should be understood as an averaged over, say, the conformal dimension of operator 1 within a window.
Correct. Yeah, so we have to sort of decide some kind of window around the delta, and then basically this is the result where after you average the 3-point function over this window, summing over all possible operator in that window.
But
So
L is fixed.
L is fixed. L is quantized. So, but delta is smeared out. Well, L is also quantized, smeared over in some sense, because we are considering the limit when I think delta and the L and the deltas are large with this behavior. So I think L is also smeared in that sense, because we are calculating this for fixed beta and fixed omega, and we are doing inverse Laplace transform of this calculation. So yeah, so I think that both L and delta are smeared with small window.
So, but these formulas can be do not depend on the central charge being. I'm talking about 2 dimensions. On the central
Well,
charge
so
being
F
large
is
or
related
small.
to central charge.
Mhm.
Yeah, so but central charge, F is the only quantity that sort of depends on, tells you what's.
So they're valid also for small central charge.
What do you mean small central charge?
C in 2 dimensions equal to 1 to 24. Now I was thinking whether one could see the same behavior for, say, 3-point functions or entanglement entropies in, I don't know, in an extremal CFT.
Okay.
We know that a small central charge, we know that they exist because the deltas are quantized, right? They're integers.
Right.
So I wonder if you get exactly the same behavior when the deltas are large in theories where deltas are quantized.
Well, so we are considering the limit when delta is large, so I'm not sure whether I can see the distinction. If delta is quantized by integers, for large deltas, I'm not sure I can tell.
So also the uncertainty on the delta should be much larger than 1. I mean, you're averaging the 3 deltas over some interval, and you say that also the interval should be much larger than 1.
Yeah, 1 in the unit of the 1 in the size of the Cauchy surface. Yeah, yeah. Yeah, I think so. Because this formula is valid when the temperature is much, so beta is much smaller than the size of the Cauchy surface.
Mm-hmm.
And so, yeah, so what does it mean? So that means that we are assuming that the energy is a continuous function more up to the size of, yes, I need to think. So how, yeah, you're asking how precisely is the size of the window?
Yes, and we distinguish, because I mean, we have free theories that we could check. I mean,
so my guess is that so it's the inverse size of the Cauchy surface.
I guess the question is, does the formula apply to minimal models, for instance, or no?
Applies to minimal models, applies to free theories, applies to
It does. I'm not assuming she's large, well, F is large. I'm assuming temperature is large.
Yeah. So in order, maybe the question is indeed, what is this 3-point function? Is it, can you, if you have some quantization in the levels, as it happens in many theories, say free theories, is this delta, is the average larger than the inverse size of the Cauchy surface, or
yes, yeah.
Much larger than the Cauchy surface?
So yeah, so the question you might be asking is when she is large, whether the gap, the size of the window scales are in C or not, for example, 1 over C or not.
Yeah.
I don't remember. So there was some discussion on this in Sasha's paper, and then there is a follow-up paper by Surdip Pal and the collaborators. I need to look up precisely where.
Because that would be important to see if this counts.
No, we didn't attempt to do that in this paper. So yeah.
Are there any more questions for Hiroshi?
There's something you can say for non-compact figures.
Yeah, so typically when conformal field theory has non-compact global symmetry, the theory is non-unitary, and so there are many things that we assumed goes wrong in for non-compact group. So for example, discrete group analog of non-compact group would be like discrete group which is not finite. So in that case, for example, this formula cannot be true because this will be infinite, right? So Yeah, so there are many things. So in this work, I assume that, so for example, the second Kashmir can be negative, for example, for non-compact group. So then this is going to exponentially grows, and that seems to be inconsistent with the convergence of this. So I think many things goes wrong, and I suspect it's because typically, if you assume that internal symmetry is non-compact, actually the conformal theory is non-unitary.
Just assume that the symmetry is broken at kind of temperature.
So that's an interesting question. So there is a suggestion that there might be a model where symmetry is spontaneously broken at finite temperature. I do not know of any theory in integer dimension and unitary.
There is one paper, right?
There is a paper by Zohar, Eliezer.
Without Zohar.
No,
Without Zohar?
It's either non-local or factorial.
It's not local.
So I'm wondering, does something goes wrong in this argument? If it is sometimes the same.
Well, so you say there is actually a paper
Non-local.
non-local.
I think it's
Unitary but
it's
non-local.
Dimarsky or something.
No, I think it's by Eliezer and but without Zohar.
But without Zohar. The one with Zohar is like
Yeah. That's for my
I
assumption.
think it's so factorial dimension.
There are some gauge theories.
It's a gauge theory, yeah.
Some papers about.
Large n, infinite n, but 1 over n correction.
Is that it?
Yeah,
I think it
it's
was
always
integer
Chandra.
dimensions, but local, but gauge theory, and I think large n.
Large n.
Only infinite n.
Yeah.
These theories are all gauge theories, but none of them are true dimensions that are unitary.
No, but there's also like non-gauge, like O and
There are all
This theory is conformal at large
Well,
temperature because it's also.
Yeah, so that's another question. There can be quantum field theory where high energy limit is not conformal. You can have some pathological situation.
But I mean, I was asking whether it's possible now. Just asking, was it an assumption here? Or
The assumption is unitarity and locality.
the fact that if the symmetry is broken spontaneously at finite temperature, I mean, you would have some.
Well, I'm
zero
assuming
modes, I
that
guess.
symmetry is acting on the Hilbert space. So when symmetry is spontaneously broken, then the symmetry generator does not act on the Hilbert space.
Right. So, okay, so it's
That's another
so it's
assumption.
hidden.
That's an assumption. I'm assuming that we're considering conformal field theory with the unitary and local because I'm using summer effective field theory, and also assuming that symmetry is represented unitarily on the Hilbert space.
Yeah.
Okay.
That's 10.
All right. Thank you.
So yeah, you know, interesting about this.